Imagine two heavy-duty table saws side by side in a workshop. You plug them both in, and, well, they are pulling the exact same amount of electrical current from the wall.
Right, identical current.
Yeah. And you feed a thick piece of hardwood into the first one, and the blade just bogs down. I mean, it's whining, it's struggling to get through the wood.
We have all heard that terrible sound.
Exactly. But then you feed an identical piece of wood into the second saw, and it tears through that hardwood like absolute butter.
Wow.
Same current, totally different outcome. And the secret difference between the two, it actually comes down to a single number in a very specific equation that's hiding inside the casing.
It's really the unseen architecture of the physical world. I mean, as consumers, we are so conditioned to just glance at a spec sheet, see a bigger number on the box, and assume, oh, we are getting a more capable machine.
Right, bigger is better.
Exactly. But when you look closely at the interplay of volts, amps, and horsepower, you start to realize that mechanical force isn't just about how much electricity you consume. It is entirely about how that electricity is leveraged.
Which is exactly why we are diving into this today. Welcome in. Today, our mission is to completely decode the mechanics of power using this fascinating stack of source material we've gathered titled Visualizing the Horsepower Equation.
It's a great document.
It really is. I mean, we are surrounded by motors every single day, but the actual numbers that dictate how they work usually feel, totally abstract.
Oh, like a foreign language.
Right. So today, we are cracking that code for you. Because understanding this means understanding the literal translation of invisible electrical energy into tangible mechanical work.
And at the absolute center of our sources today is one fundamental equation. It's basically the mathematical heart of matter. Horsepower equals EMF times current divided by 746.
Okay, let's unpack this. Horsepower equals EMF times current divided by 746.
Rolls right off the tongue.
Right. I mean, it sounds like high school physics, but
yeah,
it is actually the formula for making things move in reality. And to understand how that translation happens, we have to isolate the variables.
Yeah, break it down.
Exactly. Our sources break this down by looking at the dependent and independent variables. So first, we have horsepower, or HP. That is our dependent variable.
Right, because horsepower doesn't just exist in a vacuum, You don't have a bucket of horsepower just sitting in the corner of your garage.
I wish I did.
Yeah, me too. But it's a dependent output. It is entirely at the mercy of the electrical inputs you feed into the system. You create it by manipulating other factors.
So it's basically the end of the assembly line.
Exactly.
So what is it depending on? That brings us to our independent variables. These are the two inputs you actually get to manipulate. EMF, which stands for electromotive force, and current.
These are the raw electrical realities. EMF is what we measure in volts, and current is what we measure in amps. And together, they dictate the total electrical power entering the motor.
So let's visualize how they work together. Because, as anyone who has ever tripped a circuit breaker knows, current is just one side of the coin.
Very true.
And instead of falling back on that, tired old plumbing analogy of water in a hose.
Oh, please, let's skip the water analogy.
Right. Let's think about this like the drivetrain of a bicycle.
Okay, I like that.
EMF, that electromotive force, is like the size of the gear you are using. It's the potential leverage. It is the physical push.
That's a great way to conceptualize it. It's the pressure driving the entire system forward.
And current, the amps, that is your pedaling speed. It's the actual flow of work being done within that leverage.
Yeah.
Because if you have a huge gear so high EMF, but you aren't pedaling zero current well, you aren't going anywhere.
You're just sitting still. You need both the push of the gear and the flow of the pedaling to generate power. And if you multiply the EMF by the current, you get your total electrical output in watts.
But here is where we hit a really fascinating mechanical roadblock in the source material. Your electrical system is generating watts.
Mm-hmm.
But the saw blade cutting the wood, that isn't measured in watts.
No, it's measured in mechanical horsepower.
Right. You have electrical energy on one side of the motor and physical lifting, spinning, tearing force on the other. They are just two entirely different languages of power.
Totally different.
Which brings me to the biggest question I had when I was looking through our research. I see the top of the equation, right? EMF times current.
Yeah.
And I see that it outputs horsepower. But then there's the bottom half of the equation. We are instructed to divide the whole thing by a constant factor of 746.
Ah, yes. The 746.
Why that specific number? I mean, it feels like a random magic number someone just pulled out of a hat.
Yeah.
Why divide by 746?
It looks completely arbitrary, I know, but it's actually deeply rooted in the history of the Industrial Revolution. It goes all the way back to James Watt.
The steam engine guy.
The very same.
Mm-hmm.
When Watt was trying to sell his newly improved steam engines, he had a massive marketing problem.
Oh, really?
Yeah, his customers were mine owners, and they didn't know what a steam engine was. I mean, this was new technology. They only knew how much coal a draft horse could pull out of a mine in a single day.
Oh, so he had to translate the power of his machine into a metric his customers already understood.
Exactly.
The literal power of a horse.
Yeah, literal horsepower. Watt calculated that a strong draft horse could lift 33,000 pounds of coal 1 foot in the air in 1 minute.
Okay.
Or if you break that down to a per second basis, it's 550 foot-pounds per second. That became the gold standard. 1 mechanical horsepower equals 550 foot-pounds of work per second.
Wait, okay, but how does the physical lifting of coal connect to an electrical equation?
Well, through the joule. Fast forward to the electrical age. We measure electrical energy in joules. 1 watt of electrical power is defined as 1 joule of energy flowing per second.
Right, okay.
So when physicists eventually sat down to calculate the exchange rate to find out exactly how much electrical energy was required to replicate the physical work of James Watt's horse lifting 550 pounds, the math yielded a perfect, immutable constant.
And that's the number.
That's the number. It takes exactly 746 joules of electrical energy per second to produce 1 mechanical horsepower.
Oh, wow. That is incredible. So 746 isn't just an arbitrary divisor at all.
Not at all.
It's the exact physical bridge between electrical potential and mechanical reality. It's like the literal exchange rate of physics.
Without it, you just have a pile of electrical energy and no way to quantify what it can physically lift or spin or push.
Yeah.
The 746 is what translates the invisible into the tangible.
So now we have our complete cast of characters. We have our dependent output in horsepower, our independent inputs in EMF and current, and our historical physical translator in the constant 746. So let's see what this actually looks like when we fire up a machine. Our source material visualizes this relationship on a graph, but rather than just, reading coordinates off a piece of paper, let's imagine you and I are standing in front of a massive industrial motor.
I love it. Let's do it.
And on the control panel for this motor, we have two heavy steel dials. One controls the voltage, the EMF. Exactly. And the other controls the amperage, the current.
The flow.
And right above them is a bright digital readout showing our output in horsepower.
Okay, so let's run the first scenario from our sources. We are going to lock the voltage dial at 110 volts.
Oh yeah, 110.
Yeah, this is the baseline. It represents the standard push you get out of a normal household wall outlet.
So we have the voltage locked. Now let's grab the amperage dial, the flow. Right now it is at 0, and our horsepower readout is, unsurprisingly, at 0.
Makes sense.
But as I slowly twist that current dial up to 5 amps, you can hear the motor start to hum. At exactly 5 amps, keeping the push at 110 volts, the readout clicks to approximately 0.74 horsepower.
Which perfectly validates our equation. 110 times 5 divided by 746 gives us exactly that output.
Now I'm going to twist the amperage dial even further. I'm going to double the flow. I crank it up to 10 amps. The motor gets louder, the spin gets faster, and the digital readout climbs to approximately 1.47 horsepower.
And what you are witnessing there on the readout is what our research defines as a direct linear relationship.
A direct linear relationship.
Right. Because the voltage remained entirely constant, every single amp you added to the system yielded the exact same predictable bump in horsepower.
Yeah, because 0.74 doubled is 1.48. So we're seeing a nearly perfect doubling of the output just by doubling the current.
Exactly.
But the marvel here isn't just that 2 times 2 is 4. I mean, the marvel is the absolute reliability of the physics. As long as your voltage is locked, every single amp of current works exactly as hard as the last one. It is a perfectly steady, proportional climb.
It is reliable, yes, but it's also limiting because you are stuck on a very shallow trajectory. You are getting a steady climb, but you aren't getting a dramatic one.
Which brings us back to our 2 table saws from the beginning of the deep dive. We've seen what happens when we increase the flow, the current. But what happens if we dramatically increase the push?
Right.
What if we step away from the standard household outlet and crank up the EMF?
This is where we shift from standard consumer tools to heavy-duty engineering.
So I'm going to reach over to the control panel and grab the voltage dial. I'm taking it from 110 volts, and I'm twisting it hard to 220 volts. We have doubled the electromotive force. We have doubled the push.
And we are going to leave the amperage dial exactly where it was. We are keeping it locked at 10 amps, so the flow is identical to the last scenario.
But the output is completely different. We trace that same 10 amps of flow through the new 220-volt system, and our digital readout leaps from 1.47 horsepower all the way to roughly 2.95 horsepower.
And that phenomenon right there is the core insight of the entire source document. They call it slope sensitivity.
Okay, let's dig into that because here's where it gets really interesting. We are looking at 2 scenarios, pulling the exact same amount of current 10 amps. The volume of electrical flow is identical.
Right.
But simply by doubling the voltage, the push, we have doubled the physical mechanical output without adding a single extra drop of current.
That is slope sensitivity. In the math, it means that the higher your EMF, the steeper the functional line becomes on a graph. But in actual physics, it means that higher voltage makes the entire mechanical system wildly sensitive to current.
Wait, does this mean that a higher voltage makes every single amp work significantly harder?
Precisely. Because the EMF and the current are multipliers of each other. When you make the EMF multiplier bigger, you fundamentally change the geometry of the power generation. 1 amp of current at 220 volts does vastly more physical work than 1 amp of current at 110 volts.
Oh wait, let me push back on this for a second. If higher voltage does all the heavy lifting and it makes every amp work so much harder, why do we bother with 110 or 220 volts at all?
What do you mean?
Well, why don't engineers just wire every house and every tool for, 1,000 volts? We could use tiny, cheap wires and get massive horsepower out of everything.
It's a brilliant question, and it goes straight to the heart of real-world physical constraints. It is essentially a battle between insulation and copper.
Insulation and copper.
Yeah. High voltage, that massive push is incredibly aggressive. It wants to jump out of the wire. It causes earthing. To safely contain 1,000 volts, you need incredibly thick, heavy rubber insulation or massive physical distance between components.
Which I imagine isn't really practical for a handheld drill or a blender.
Not at all. It would be huge and dangerous.
Okay, so voltage requires thick insulation for safety. But what about the current?
Well, current requires thick copper to manage the heat. The more amps you try to force through a wire, the hotter it gets. If you try to run a heavy industrial saw at a low voltage like 110, the slope sensitivity is so shallow that you would need to pull a massive, dangerous amount of current, literally dozens of amps, just to generate the required horsepower.
Oh, I see. You would need a copper power cable the size of a water main just to keep it from melting into a puddle on the floor.
Exactly. And copper is heavy, and it is expensive. So engineers have to strike a balance. By bumping the voltage up to 220, they change the slope sensitivity. They make the machine highly sensitive to the current, which allows them to hit huge horsepower numbers while keeping the actual current flow incredibly low.
That immediately makes me think of what is happening right now in the electric vehicle industry.
Oh, definitely.
I mean, if you follow EV tech, you know that the biggest buzzword of the last few years has been 800-volt architecture. Companies like Porsche and Hyundai are building cars on 800-volt systems instead of the older 400-volt standard.
It's the exact same math, just scaled up to automotive proportions. It is slope sensitivity in action.
Because in an electric car, weight is your absolute worst enemy. If you build a car on a 400-volt system and you want to generate, say, 500 mechanical horsepower to get off the starting line quickly, you need a tremendous amount of current flowing from the battery to the motors.
And as we established, massive current requires massive copper cables to prevent the wiring harness from melting.
Right.
You'd have hundreds of pounds of heavy copper snaking through the chassis of the car.
But if you double the voltage, if you jump to an 800-volt architecture, you radically steepen the slope sensitivity. Suddenly, your electric motors are extracting double the horsepower from every single amp.
Which means the engineers can slash the current requirements in half while hitting the exact same horsepower numbers.
And having the current means you can cut the thickness of the copper cables in half.
Exactly.
You save hundreds of pounds of weight. The vehicle gets lighter, the motors run cooler, and the car goes faster. All because they manipulated the EMF variable in our equation to change the slope sensitivity.
It really highlights how elegant the physics can be when you actually understand the mechanics behind the numbers. You aren't just adding power, you are completely redesigning the efficiency of the physical transmission.
It fundamentally changes how you look at the specs. Think back to those two table saws we talked about at the very beginning.
The ones that sounded so different.
Yeah, they were pulling the same current, but one was choking and one was cutting like a laser. Now we know why. The second saw was wired for 220 volts. It was using a steeper slope sensitivity to extract drastically more mechanical force out of the exact same 10 amps.
It's amazing when it clicks. We established the dependent output, our horsepower. We saw how EMF and current act as the independent inputs, the dials we can actually twist.
We took a detour through the 18th century to understand why 746 isn't a magic number, but rather the literal historical bridge perfectly translating electrical joules into James Watt's mechanical lifting force.
And finally, we saw the physical reality of the math. How a locked voltage creates a predictable linear relationship, and how doubling that voltage aggressively maximizes the power of every single amp in the system.
So the next time you're buying a tool or researching an electric vehicle or looking at an appliance, you aren't going to be blinded by the marketing fluff. You are going to look at the volts and the amps, and you're going to see the beautiful proportional math happening right beneath the casing.
You'll see the truth.
You really will. You will understand exactly how this system is uniting push and flow to create that mechanical reality.
You've essentially learned to read the underlying language of the machine.
But as we wrap up this deep dive, I want to leave you with a final thought to mull over that builds on everything we've unpacked today. The equation we've been looking at, EMF times current divided by 746, is theoretical perfection.
Yes, it is.
It is a mathematical absolute. It tells us exactly what the mechanical output should be in a perfect universe. But as we all know, we live in the physical world. And in the physical world, thermodynamics always demands a cut.
Always. No system in reality is perfectly efficient.
Exactly. When a real motor fires up, the casing gets hot. The steel bearings rub against each other. The whining sound of the motor vibrates through the air. All of that heat, that friction, that sound, that is energy physically escaping from the motor.
It's lost.
Yeah, it is electrical energy that is explicitly not becoming horsepower. So think about this. If the math we just learned tells us exactly what the mechanical output should be in a perfect vacuum, how much extra electrical juice do engineers actually have to pump into real-world machines just to overcome the physical realities of friction?
It's a great question.
Just to hit those perfect numbers printed on the side of the box. It is a constant battle against thermodynamics, and it makes you wonder just how hard these machines are really working behind the scenes. Thanks for joining us on this deep dive. We'll catch you next time.